Basically, I will be presenting the work that I did as part of my Erasmus at Central Supalec and within CIDRE. And now the rest of the work until the delivery of my thesis. This work is based on the PhD of David, which was a student supervised also by Michel Lafont. And we will be focusing on adapting a network intrusion detection system into a different approach that uses pickup captures instead of application logs, which was implemented by David during his PhD. And we are trying to see how we can make the IDS more effective using a multi-modèle approach. So this is a very simple introduction to the model itself and how the models are being built and why they are interesting actually. So here we have a very simple distributed system which has just two processes. The first process, the only thing it does basically is send a message through channel 1 with the message M, and every time process 2 receives the message, it launches a process that increases a counter. So it's the I process is basically a counter for all the messages it has received from process 1. And normally this is a distribution computation cut and as a particular set of it has a particular order to which we follow the events. So for example, here we can see that these two events, so the sending of C1 of the message M on C1, two events happened before the first message was received, but it could also very actually be that the P2 channel received the message before the sending. So it's a bit arbitrary, and that's why it makes it interesting, because we can create these structures, as you can see on the right, which are called lattices. And these lattices allow some sort of understanding of the distributed system, as well as retaining not only the partial order, but understanding the possible concurrency of the events. So for example, here in this case, each axis is a process, and you will have as many axes as you have processes in your distributed system. And here we can see that in the first state, or the first combination of the events, the only event that can occur is the sending of the message, because process 2 is dependent on having received the message to launch any other of the processes it has, so process I in this case. So once you send the message M from P1, then you have a lot more choices, and you can either send another message M, which is what happens here. So you have two messages before you have the receive event. But you can also just send a message and also receive it right away, and then count run the counter for the receiving of the message. And basically what this structure is encoding, let's say, is all the possible concurrency that can happen within this. And it's maintaining the partial order of all the events. So for example, here in the structure, you cannot receive a message before sending one. So you cannot start going up here, because that will be impossible. And there is certain rules on the partial order that need to be maintained. And these structures, the lattices, are very good at doing that. As you can see as well, there's a few special elements, which we call multi-reducible elements. And basically, the simple definition for these elements is that there is only one possible event that can occur to get out of these states. So if you can look into all of them, there's only one event occurring out. There's possibly two entering, but only one out. And this is a very interesting point in the state, because if, for example, we go through this line here, so through this in which C1 sends P1 sends a message M, then it is immediately received, and then the counter is run. Now we are in sort of a halt of the distributed system, because P2 cannot run any longer because it is dependent on P1. So the only thing that can occur in this distributed system really is that P1 sends another message. And if it doesn't, then the computation really stops, because P1 can only run things as long as P2, sorry, can only run things as long as P1 keeps sending messages. So as you can see, there's a bit of dependency between the processes, and this structure, while very simple, allows to capture the essence of the computation, the partial order, and the concurrency in this distributed system. That's why it's very interesting. And from a computational point of view, it's a very easy structure to compute. So that makes it a bit more interesting to search how we can use these structures to understand the behavior of the distributed system themselves, and possibly use models that we create of its behavior to create an intrusion detection system. So here you have a simple presentation of the type of models that were built using the lattice. As I said in the beginning, it's a multi-model approach, but the fact is that both the two models that we are using are derived from the same structure, which is the lattice. So the first model is a simple automaton. Is in his PhD, David made a more complex automaton, as we are used to see, with a lot of states and dependency between the events. And if an event occurs out of order, then it's some sort of violation of the normal behavior of the system. But here, what we decided, taking into account that we are moving into a pure network scenario in which there's just thousands and thousands of packets going in and out, and we don't really know if, for example, a bit of delay in one means that the automaton will be respected, and also because the other model is also very complementary to what a full automaton would be able to do. We have decided to do a simplification. So the most absurd simplification you can do, that is to reduce the automaton to one single state. And this single state accepts all the events that that are known for the system. So in this case, the events are just the sending and the receiving of the messages through channel 1. The event A, which is occurring here on P1, and then the event I, which is the counter that we were discussing about. And in sum, this automaton is just a simple filter that filters all the known events and everything that we don't really know what it is. So, for example, if you had, let's say, an event B or a message from P1 to P2, but through another channel, that would be unknown to the automaton and would be marked as a violation because it never saw it during the training of the model itself. And then the second model, which is arguably a bit more interesting, is called invariant lists. And it's basically a set of rules based on temporal logic that try to define the behavior of the model based on the lattice. So here we can see that, for example, a few of the invariants that could have been derived are that the sending of the message M through C1 is always followed by the receivance of the message. Sorry, actually this is incorrect. It's the other way around. So the receiving is always followed by the sending. Then we have that that I is always followed by the sending of the message. So for example, here we can very confidently say that every time there is a receiving of the message on channel 1, that a counter occurs, and that is something that is consistent throughout the entire system. So it's some sort of rule that we can create saying that this is actually happens. And here we have sort of an outlier. There's only one event A. And what we can do is that A always precedes C1 M because it is really the only occurrence that we have. And in this occurrence, it always precedes the sending of the message. So it's possibly a rule that we can also create. And in some, as I was saying, the invariants actually define the behavior of the model between the events. And while the automaton kind of does a simple filtering of what do we know and what we don't, the invariants are more looking into the actual behavior and trying to understand if what is happening within the model is known or not. And that is why the training of the models themselves is very important. For example, here we have this event A, but this event can actually be completely independent on process 1. It can be something that just happens randomly, and we created this invariant. A always precedes the sending of the message. That can be so a false invariant. It really isn't an invariant. It is an invariant just based on the data that we use to train. So as most of these types of systems, the more you train the model, the more accurate the invariance will be, and more importantly, the less invariance you have, which is curious because so as long as you are adding more information, some invariants will start losing their meaning, and only the real fundamental ones will remain in the models. So that's an interesting take on these lattices models. So regarding the categories of invariants, David actually investigated these 4 categories, which we will be using, and this is what basically the 4 types that I used for my internship and now during my thesis. The first one is always followed by, and you say that A is always followed by if B always appears after A. So it basically says that the event A is always followed by the event B. So anytime that event A occurs, then B also occurs. It doesn't need to mean that it occurs right after and it's the next event, but it eventually occurs within the system. Then we have always preceded by. So the event A is always preceded by if B always appears before A. So it's also very simple in a sense. It's of course, just logic rules, and it can take a bit to actually capture the meaning of them. But once you get it, it's quite easy to understand the rules that are being defined. The next one is never followed by, and it's very simple. So A is never followed by B. Anytime there is A, the event B never occurs in the system anymore. And the last one is a bit more complex, and it's an invariant that was a bit that was also investigated by David and a bit experimental, let's say. And it says that and it's first followed by last. And basically what we say is that the event A is first followed by last B. If the first event A, so the first event ever A that occurs, is followed by the last occurrence of B. So, for example, if we have event A occurring after the last B, then this invariant would not be verified, let's say. So, David did an implementation of all these models, so both the automaton and the invariant models, on a file distributed system called XtreemFS, and he used very simple notions of messages. So the type of events that he used was, as you can see here, so the sending of a message through a given channel or given certain IDs to processes like A or B or C. But we wanted to do this on a very large scale and for packet captures, as I was saying. So the network aspect of it makes it a lot more complex because if we want to adapt this model to any type of network or to a larger type of networks at least, then we cannot have such a, let's say, such a rigorous approach to the events, and we have to create a way of defining them a bit more largely and that can be encoded at a large scale. So for this adaptation, which was literally the focus of my thesis, the interesting features that we were considering are basically what defines a connection in TCP/IP. So the IPs and the respective ports. And we decided to use this just because, as I was saying, they are the essence of what defines a connection. So if you don't have the IPs or the ports, you cannot really say that a message traveled from A to B because you don't know A and you don't know B. So you know that a message traveled, and within a lot of the newer machine learning based intrusion detection systems, they are using a bit more obscure features such as the flow rate and the number of backward packets and forward packets. But in this case, we wanted to remain within the very basic notion of what a connection is. That's what it was important for us to keep these basic these basic notions. And for the event definitions, we based on 4 main categories. So the number of actors. Are we considering only the source or the destination, or are we considering both? We decided to also go with using the IP or only a keyword. So we know that an event is internal or external, or use the IP. Then the TCP UDP ports. And here we can have the port itself, or we can have just the special ports defined by the IANA. And then we can also apply an operator to the model, to a module operator on the ports in order to have a reduced number of events at the end. And here you have a few examples of events. So here you have two IP, so you can say that this is the source IP, the destination part, the source port, the destination IP, and the destination port. Here you have either the source or destination keyword and the port. And here you have the both keywords, and this one is the source part. So these are a bit of the defined events, but a lot more events have been defined. I think there are 31 different type of events using or basically playing with all these categories that were defined. I'll try to go a bit more quickly. So the dataset that we used was the CIC IDS 2017. It is a dataset with 5 days of pickup captures, and it basically tries to mimic a workday in the office. And it goes so Monday through Friday from 9 a.m. until 5 p.m. And basically, the Monday traffic contains only normal traffic, so it's benign for the training of the models. And the rest of the days contains attacks both in the morning and in the afternoon. And as you can see, the attacks are very different between each other. So we have denial of service, RP attacks, web attacks, infiltration attacks, botnet. So it's a very diverse set of attacks, and allows us to also have a better idea of what the models can be good at in a large scale. And the dataset consists of both the pickups and then labeled connection logs generated by a tool they created called CIC Flowmeter. And these labeled connection logs are basically the connections and the respective logs, so benign or malicious. And it's what we can do to match between the model's results and the actual results as labeled per the dataset. But we found a big problem with this dataset, and also the other datasets that we considered didn't fix this or also didn't allow for this. And the big problem was that the connection logs are faulty, because they provide a timestamp without enough accuracy. And we saw this happen also for example, KDD and dataset IoT 23. They don't really account for, so in the case of KDD, you don't even have the pickups. And for the other, they don't account for the fact that someone might be interested in establishing these very basic notions of connection and the respective label. So for example, for the CIC IDS, we have a given packet that has a very specific Unix timestamp in milliseconds, as we all know. But then the connection label is something very generic like this. So it says this is for the same timestamp. Instead of having this number that is very precise, we just have that it happened on the 7th of July of 2017 at 12:45, and that the connection lasted for 501 milliseconds. So the question that is posed now is, when did the connection start? So does it start at 12:45:00? Does it start at 7 milliseconds, or somewhere in between? And we don't really know, because there is no labels for each individual packet. There are for connections, and we don't really know precisely when the connection starts. So there is a problem. And for the specific models that we are trying to understand and trying to evaluate, the models require a precision in how you match the packets and the respective label, which we don't really have. So the end result of this is that we have some sort of a margin of error. There is between 0 and 60 seconds. that can't be calculated in practical terms. So here we have that 12:45 minutes, 12 hours and 45 minutes, but we don't know the seconds that it started, and we also don't know the milliseconds, which would even be also good to know. So just be aware that there is this margin of error, and that it kind of makes either things a bit harder to calculate or the results a bit. So going into the results, here for the automaton models that we created, we have the code. So each code is a definition of events. And here you have some type of events that might be interesting. I think due to time, maybe it's not worth going into detail on this. But here the result, of course, is that the more complex the definition of the event you have, the more events you will have, and in some you will let's say harvest a more defined behavior of the model, and you have more detail of the events that have occurred within the model. So you can see in this case of the 53 of the code 53, which is one of the highest ones in terms of number of events generated. The definition is the source IP, the destination IP, and then the part. And you can see that it generated over 200,000 events. But then for other type of events like 22, it only generated 4 because it's using only the keywords, so internal or external, and the special part, which is just a few of the known parts in TCP/UDP, like port 80 or port 22 that we all know of. Then so this is for the actual results of the detection. The best performance was for the port scan and denial of service, distributed denial of service attacks on Friday afternoon. And you can see here the absurdity of the results. So the accuracy and the F1 score are over 1, which is literally impossible. And the problem, or why this is happening, is because of that margin of error that I was talking about, that we don't know when the connection label started. So we are considering that it starts at 12:44:00:00. And actually for these results, we are still considering a period. So we added a period to the duration of the connection. That is so 59.99 seconds, in order to capture a window that we can make sure that contains all the labels, all the connections. But we also introduce an error that we cannot really control. But nevertheless, we can create a comparative result between the different models. So we can for sure say that the automaton models were really poor in detecting the web attacks, and that is normal because they use the same types of connections. That makes sense. And it's also very bad at detecting the botnet attacks because the F1 scores are just really bad. As you can see, the accuracy remains high throughout, and that might give you the idea that the models are actually good, but it's just the fact that there's so much class imbalance. The number of malicious packets is much lower than the actual number of benign packets. So it means that regardless of the results, almost the accuracy will remain high. So in sum, for the automatons, the models are actually mediocre. None of them are particularly good. You have some that have around 60% of the F1 score, which means they're actually a bit accurate and they are detecting something, but not really enough to be actually good. This part here of the detection for the port scan and DDoS, which had very good results, requires a bit more understanding to have a bit more precise results, actually. For the invariant results, there's not much to say. So here you have the distribution of all the types of invariants. So you can see that throughout all the definitions of events, the distribution is more or less the same. The always followed by invariants are around 25%. Always preceded by invariants are also 24, 25%. The NFB are followed by, they are very, very low. So you can see the maximum is here, which is 5.49%. So there's very little of these invariants being created. And then the first followed by last account for around 40 to 50% of all the invariants generated. The only other interesting point here is that there is an exponential growth in the invariants as more events you have. So, for example, here you can see we have 16 events and 488, 72 events, and then we already have almost 10,000. And when we have, for example, 1,400 events, then we end up with 3 million invariants. So it has some sort of exponential growth based on a number of events. And that is because once you have more detailed events, you allow for more specific connections to be built within invariants and greater detail to be absorbed into the models. And this is the results for the invariant models. The NFB and the first followed by last offered really little to no benefit. They showed very low F1 scores and also very low precisions, which were both below 5% for all cases, for all the days of attacks. So over 10 type of attacks. And on the other hand, the AFB and APB kind of have had better results. So for the F1 score, it was around 25, which is still very bad, with the exception of the ArtBleed attack and infiltration attacks. So ArtBleed was on Wednesday and infiltration on Thursday, which had very good results. But again, you can see here the absurdity of these values because they are over F1. They are over 1, sorry. But you can see here that comparatively, or in a qualitative way, we can say that these attacks were better detected than the others. So what is next? So until the end of my thesis, the two questions that I'm still trying to answer is, are the models actually complementary? So having derived from the same mathematical structure, which is the lattices, if they are complementing each other or they are basically looking into the same things. So we have the invariant and automaton models that derive from the same structure, but we want to understand if what they are detecting here is the same that they are detecting in the invariant models, or if somehow they are detecting different things, and once you merge them together, you obtain better and improved results, which would be very interesting. And then how do the results change when the models are trained with more data using the David's generalization mechanisms for the model? So David created also or developed generalization mechanisms for if you have multiple intermediary models, you can just merge them together with specific rules for both for the automata and for the invariants. I will also be trying to understand if those models behave better, because as I said in the beginning, if you have more data, you have less invariance, so the models are much more precise at least. And then regarding possible future work is to explore other definitions of events using other information, to experiment a connection log-based approach instead of the pickup, So the error that we have here is because we are using pickups and then trying to match each packet to the respective connection on the label that they provide, on the log they provide. So maybe we can also try to directly train the models with the logs and then see how how they behave, and then try more robust ways of generating the invariants supported by other machine learning techniques.